Okay, so let's look at this second exercise we have here. So it says create a custom classifier that will always predict the majority class of the training data. Then afterwards extend this class to have the predict problem method, a method that returns the probabilistic values using the distribution of classes in your training data. So let's do the first part and then we'll do the second part. So for classification, classification is a branch of supervised machine learning where we're trying to predict what class an observation resides in, what class does it belong to. These are discrete values. Think of image classification. If we have an image, we have a classifier. We're trying to determine if it's one image or if it's one particular type of image. Is it a pipe or is it not a pipe? Is it a cat, is it a dog, or is it a rabbit? Predict distinct classes for our observations. So the California housing data, that is a data set we use for regression. So let's first import a data set we can play around with to test out this custom classifier with. So from there, I'm going to use the wine data set. Alright, so load, where is that? Load wine data. Alright, so then we can go ahead and say data equals to load wine. Very similar syntax as before. Okay, let's run this cell. All right, seems to work. Let's look at X. So we have X there. Let's see the shape of it. Right, so it's a data set of 178 observations with 13 columns. In other words, 13 attributes for each observation. We look at Y. Notice Y we have 0, 1, and 2, so we have 3 classes. So there's 3 different classes each observation belongs in. Now the purpose behind this majority class classifier is when working with classification, we want to make sure that our model does better than some benchmark model. And a very naive benchmark model is a model that always predicts the majority class. Going back to the example of image classification, if a lot of your images are pipes, then a very naive model will always predict an image is a pipe. So we want to make sure any model we create does better than that benchmark. So let's go ahead and start defining this classifier. So I want to make sure we import the proper things. So do scikit-learn base. We're going to import the classifier mixin. Before we use the regressor mixin, we want to make a classifier, so we'll import the classifier mixin. Okay, let's run this cell and let's start creating that custom class. Okay, so I'll say class. I'm going to call it majority classifier. It's going to inherit the base estimator as well as a classifier mixin. Define the init method. Let's think about it. Are there any variables we need to initialize? Any attributes we want our object to have when we create the object from this class? I can't think of any, so we'll just go ahead and have it blank, but if we want to leave it blank, we got to make sure we type in pass as a placeholder. We can always just omit it, but I like to keep it there. Okay, now let's define our fit method. So fit's going to take an X and a Y. So let's think about what needs to undergo in this fit method. What do we need to calculate before we're able to make predictions? That's what's going to happen in the fit method. We got to think about what do we need to do, what things do we need to calculate and determine so we can make predictions. What do you guys think? Well, we want to determine what is the most common class of our training data, which one is the most frequent, which class appears the most often. Because if we determine that during the fitting process, then we can use that value every time we make a prediction. So we got to put here in this method how we go about calculating the most common class in our training data. Now there are several ways to do this, to accomplish this. I'm going to offer one way. You can go ahead and do it a different way, so there's nothing wrong if you have a different manner. But for this, I'm going to exploit the collections library that Python has. So go ahead and open up a new cell here. So from collections, import counter. So counter is a nice class we can use to do some counting of values very easily. We can always program this ourselves, no problem, but let's use a built-in tool that Python has to offer us. Import the counter. Let's go ahead and look at the documentation. Let's look at what the documentation says about this counter. So I'm going to put the question mark there. We're going to run this cell. Let's see what documentation comes out. So let's analyze this doc string. So it's a dict subclass for counting hashable items, sometimes called a bag or multi-set. Elements are stored as a dictionary keys, and their counts are stored as dictionary values. So what this counter is going to do, it's going to go through something. In this example, they show us it's a string of A, B, and C, and D, and it's going to go about and counting the number of times A occurs, the number of times B occurs, the number of times C and D occur, and it's going to return you a dictionary-like object that you can go ahead and use to determine, okay, how many times did A appear? How many times did B appear? So the key will be the entity that was counted, and the value for that the value for that key would be the occurrences, number of occurrences. So this is something we'd like to use. Because what we're going to do is we're going to pass this label, this Y. We want to be able to count how many times 0 appears, how many times class 1 appears, and how many times class 2 appears. We want to identify those counts. We can program this ourselves, but let's go ahead and use this built-in tool called counter. So we can look at some usage of it. So sometimes you might want to look at this documentation if you haven't played around with this class here that Python has to offer you. But looking at it, this seems to do what we want to do. Let's go ahead and implement it. All right, so I imported counter. So that's what I'm going to do in the fit method. I'm going to see C equals counter. I'm going to pass the label set, the true answer for our observations. And actually, let's do this outside. Let's play around with it. So I'm going to say counter of Y equals C. Okay, let's run C. Okay, so notice now I return a dictionary-like object where it says A0 occurred 59 times, 1 occurred 71, and 2 occurred 48 times. We'll actually do it a different method. Let me show you an example. I can use Boolean indices to do this. During a Boolean array, I can say Y equals 0. This will tell me number of entries, which entries had a value of 0. I can calculate the sum, and 59. So that's exactly what I had before. That's exactly what I had, this counter did. 59. If I switch it to 1, I get 71. If I switch to 2, I should get 48. And I get 48. So it's a nice sanity check showing that these two methods get the same answer. So let's just keep the counter approach. So that's what we started writing. So we have faith that's going to work out. So once we have this, we got to figure out which one occurred the most often. So let's look at some documentation. So I'm going to exploit Jupyter Notebook's tab autocomplete, see what type of methods I have available for me for this created object. So I see something that catches my interest. I see something called most common. Okay, that perhaps is something useful. That might be a method that will tell me which element, which key was the most common, had the highest count. All right, let's go ahead and open that up. Let's hit tab. I want to look at the documentation. Remember, we want to be comfortable enough to look at documentation, realize what's going on, and figure things out. So list the n most common elements and their counts from the most common to the least. If n is none, then the list will list all element counts. Okay, so it seems that the way this works, I can pass an n value and it will return to me the most common. So if I say most common 1, it will give me the most common 1. If I say most common 2, it will give me the 2 most common values. So let's try it out. Let's see what happens. So looking at these numbers, I understand that label 1 was the most common. So we're going to make sure we return that. So most common, I'm going to say 1. And notice returns me a list least what appears to be a list, of a tuple where the zero index of that tuple is the label, and the index 1 of that tuple is the number of occurrences. So I want here is the zero index of that tuple. So I'm going to go ahead and, so it looks like if I want to get the most common one, the label of the most common one, I need to specify 0, so that's going to return me the tuple, and then I want the zero index of that tuple, and there you go. And that should give us the label. Put that there. So I'm going to create this variable called mode, see most common, pass in 1, 0, and 0. Now let me ask you this. For this mode, should we somehow, we're going to make use of it later, correct? We want to make use of it during the predict method. We want to invoke this value. So given the fact that I want to use this value later on in our process, what do you think I should do with this value? What should I do with this value? I should store this value. I should store this value for our object because I want to make use of it for later. As I said before, and I will keep on saying, during the fit method goes anything we need to calculate for our predict method or for our transformation, depending what type of estimator we're constructing. So one way we can store those values for use outside of this method is by using self.mode equals the right-hand side. So now every object called majority classifier will have this mode parameter. We'll have this mode attribute after we fit it. You remember that convention? You recall that convention that I said that scikit-learn is going to invoke for attributes that it calculates after the fitting process or during the fitting process? Those end in an underscore. So let's go ahead and use that convention. That might be a nice thing to use. Self.mode there. Okay. So let's make sure we return self. Def predict. Let's define our predict method. Self x. Okay. Let's go ahead and make our prediction. So we want to make sure that whatever observation comes in, we always predict the majority class. So let's construct an array that has the number of elements, number of entries, equal to the number of observations in our data set. Number of observations in our data set is going to be the number of rows of x. So we can say x.shape. The zero index is the number of rows. It's going to multiply by self.mode underscore. And we'll return this value. Okay, let's test it out. Majority classifier. There's no parameters I need to pass it when I construct an object of my majority classifier. I'll just call that MC. Let's do MC.fit x and y and MC.predict on x. Okay. So notice all the observations predicts 1, and if I look back here, 1 indeed was a class that had the most occurrences. So this is doing what I want it to do. Or at least it appears so. Okay, so we took care of that first part of the question. And remember how we stored mode, stored the value of mode. We can go ahead and take that trained object, do mode underscore, and there it is. So this might be useful for anyone who's using this tool. They may want to inspect after the fitting process, what was the most common one? Okay, so the next part of the question, let's read it. Take a look at it again. So it says here, afterwards extend the class to have the predict problem method. A method that returns a probabilistic values using the distribution of classes in the training data. So in other words, let's say in this example there are three classes, 0, 1, and 2. Now we want to predict a probabilistic value. Instead of saying this is the class this observation belongs in, we want to return a probability that our model thinks this observation belongs in this class. Going back to the whole idea of image classification, we're trying to determine whether something's a pipe or not a pipe. A probabilistic classifier will tell us I'm 75% certain this is not a pipe, or I'm 35% certain that this indeed is a pipe. We want to return that value for our classifier. We're going to make use of the relative distributions of our labels. In other words, in this example here, 59 of our observations in our training data were of class 0. So whatever fraction that represents, that's going to be our probabilistic value for that class. So let's just look at that. So I believe you have 178 observations. So we're going to do 59 over 178. That's a value of about 0.33. So we should return a value that says for this class we're 33% certain it's class 0. And for class 1, since there's 71 occurrences, the ratio there is about 40%. So we should be 40% certain that this observation is in class 1, and then class 2 has 48 observations and about 27%. So let's go ahead and include that in our method. Let's extend our method. Sorry, extend our class. Predict. Proba self x. Okay. So I need to figure out this fraction that I manually calculated up above. Of course, I don't want to do that calculation right here during the predict proba method. It needs to be based upon the training data. So where should we put the code that we're going to use to calculate the relative fractions, the fractions of the different classes? Where should that belong in our class definition? Well, it should belong during the fit method. We need to calculate this value during the fit method, and guess what? We're going to store it as an attribute of the object. So let's put in the fit method. So here we got to calculate the fraction. There's several ways to go about doing this. But let's go back to here, the C value we created. There's a values method. It's going to return all the values, the counts. So I can do this to calculate the fraction. So I can convert this into a list. So convert it into a list. All right, and I can also convert this into a NumPy array by passing it to the array function. So the array function will take a list and convert it into a NumPy array. And this is nice because once I have that NumPy array, I can do mathematical operations on that array. I can't do that on a standard Python list. There's some limited functions there because a list can hold different data types. But we can go ahead and put in this more restricted format of a NumPy array, but we have more options in the things we can do to that array. Okay, so that will construct the array, and then we divide by the number of observations, which would be the number of rows in our data set. So this should right here, we're going to go ahead and copy this code over. So I'm going to say list of c.values. Remember, this is going to return, this right here is going to return a list of all the values of the counts. Let's convert this into a NumPy array. Make sure I have all my parentheses set. I want to avoid that problem. I want to avoid that problem. And let's divide by the shape, index 0 of the shape, which is the number of observations, and I'll call that self.fraction. So I can do it out here too, just to show you. So there's our NumPy array. the fractions of all the three classes. Makes sense since this one's the highest one and that's the value we predict during our predict method. We always predict class 1 since that's the majority class. Okay, so we define that self-fraction there, self-fraction. Alright, now let's go ahead and flesh out the predict problem method. So we'll go ahead and make use of this stored value. So now we have here, let's think about the best way to go about doing this. So we have our observations. Right, so it's n by p. And over here, I have a NumPy array. Let's say length L, where L is the number of classes we have. For this example, it's just 1, 2, 0, 1, and 2. And I can put the relative fractions. The relative fractions, or the fractions, are right there. So I want to go ahead and return a NumPy array that looks like the following. That's the fraction of class 0, the fraction of class 1, and the fraction of class 2, fraction of class 0, fraction of class 1, and fraction of class 2. And this is repeated for all n observations. So I got to figure out what's a good way to go about doing this. And there's multiple ways, but the way I decide to go about doing this is by taking a fact of matrix multiplication. If I have a matrix that's n by 1, and I multiply by a matrix of 1 by 3, since there are 3 classes in this example, then the result of the product will be in a matrix of n by 3. And this will return to me this setup we have here, where each row is exactly the same. F of 0, F of 1, and F of 2. Let's go ahead and start constructing that. So let's go ahead and do it. So MP1s generate a matrix. Number of rows is the number of observations. Okay, inhabit of column 1, and I'm also going to, same thing with the self.fraction, I'm going to invoke it here. I'm going to reshape it to have one row and 3 columns. And that gets passed into the np.dot function. So the np.dot function will perform the matrix multiplication, and that's what I want to return back when I invoke the predict problem method. Run that. Okay, syntax error. Looks like I forgot a comma right there. Okay, I believe that worked out. At least it ran. Let's run it again. Okay. The mode, that works. And let's see the predict problem method and pass x. And yep, looks like I got a type error, data type not understood. Okay, let's go ahead and investigate that. Let's see what happens there. Let's see where, okay, so the problem here wasn't able to be handled by the predict problem method. Something wrong with this line here. Okay, so let's go ahead and investigate that, see what went wrong there. Okay. MP1, so this right there is the shape. That should be it there. Yeah, so I can, this goes off my parentheses. That's what happens when you have a lot of parentheses. Sometimes it helps to break things down. Makes it a little easier to read, but if I look at the documentation, I need to pass it its shape. So I want a shape of these number of rows and 1 column. So that's the argument that gets passed to MP1s. And the second argument of the dot function is the reshape of my fraction array. Okay, that should work out. Let's go ahead and run it. And there you go. We have our predicted values. Let's do a sanity check. Let's take the shape of what's returning. So it's 178 observations, 3 columns. That should work out. Let's assign this result to y probabilistic values. So of course those probabilistic values must sum to 1 across the columns. Right? So if we add this value to this value to this value, we should get a value of 1. So let's just do that sanity check. Since I have a NumPy array, I'm going to use the sum method of this NumPy array. And since I want to apply the sum across the columns, I should specify axis equal to 1. Okay, and there you go. Nothing but 1. So it looks like it works out as I intended.